Hi.
Oh, hey.
Nice to meet you. I'm John.
Nice to meet you, John. Do you hear me and see me well?
Yes, I can hear you and see you just fine.
Okay, not too high. Maybe this is better.
Let's see. Yeah, that looks perfect. That looks great.
Very good. The light is not ideal, but this
What can you
is
do,
more
right?
spectacular.
Yeah, it's we're working with what we have right now, right?
Very good. Yeah, I can't complain. I'm in Brazil, so it's so
Yeah.
nice.
Yeah, I think that's probably better for time. How are
Yes,
things over in
absolutely. It would have been impossible.
Yeah, right.
Hey, Isha.
Hi.
Hey,
Oh,
hi.
how
Hi,
are
Tom.
you?
Hi.
So nice to
Good.
see you, Isha.
Nice to see you. Thank you for making time. I know it's a very difficult time for you.
It's a great pleasure. No, it's very good. It entertains me. So this is good. Makes me do something else and think of something else.
This is your self-care besides today.
And how are you there? Crazy times for the US, huh?
Oh my goodness.
Yeah.
Yeah.
The world is following it, full of astonishment. It's crazy. It's really crazy.
Yeah.
Yeah.
Yeah, it really is.
This is the democracy of the world. So we were all very surprised yesterday. But
It's unbelievable.
Yeah.
Yeah. Yeah, I mean, I guess the nice thing is we have a couple weeks left to sort of get through, and then
there are still things happening.
Things will improve after that. But...
It's amazing. Hello.
Hi, Cristiane. How are you doing?
Fine, and you? Nice to see you, Kirill.
Yeah, Happy New Year. Nice to see you.
You too. You too.
Where are you at? Utrecht?
No, in Brazil.
In Brazil. Okay.
Yes, I have been for more than a month now. My parents got COVID, and then I moved in and I was converted into a nurse for a while. So now
how are they doing?
Fine. It's incredible. My father is 86 and he got rid of it in 3 days.
Really?
Nothing left. For my mom, it was more critical because she has Alzheimer's. She was very weak. So she was for 2 weeks in hospital. But now she's home and she can breathe without oxygen. She can eat, but her legs got weakened and she couldn't walk. She can make a few steps. And she's improving, but yeah, it has.
Well, I mean, I have to tell you that it sounds like the best case scenario. My mother had COVID and she spent 7 weeks in the hospital, including ER and everything. Yeah, and it's. I mean, she's home. She's doing fine now, but it's a very slow recovery process. Yeah. So, like, she's even though it has been already a couple of months, she's still not back to where she was before that. So it's certainly not something to joke about.
No, certainly not. My father lost 5 kilos. So he was very sportive. He used to go every day walking and so, and then suddenly he walks for less than half an hour and he was very exhausted. So it really touches you. And I don't know how I didn't get it because I was fully exposed. You know, I was even without masks, sleeping with my mom in hospital in the same room.
Well, apparently people are most contagious before they show symptoms. So somehow, yeah. I mean, it doesn't mean that the contagion immediately goes down, but it goes down as during the course of the actual disease. So
yeah, it was amazing. So everybody got it. 7 people here around us. The other lady who was caring for her, also my sister-in-law, but somehow I avoided. I don't know yet how, but it was lucky. It was good at least.
Yeah.
Yeah.
No, it's great to hear that they're doing better now.
Exactly. Yeah.
But let me ask, should I try to share my screen to make sure that it works?
Yeah, of course.
Well, I just wanted to.
I'm sure it will, but yeah, try it.
Yes, it's always good, right, to make sure that it does. Okay, so now let me go back to the first page and get it into my slideshow.
Yeah.
Yeah, does
Yeah,
it work?
fine.
Do the full screen. Yeah, it works. Yep.
Yes. And I want also to get my laser pointer. So you can follow what I am pointing at?
Yeah.
Okay.
Yeah, definitely.
And the movie, let me see if my movie is going through. Yes, it is. And this one I need to get out of my laser to be able to get it going. It goes, right?
Yeah. That looks fine.
Very good.
Mm-hmm.
Okay. Just let it get to the end. Okay, then it's all good. Anything else you need from me? You need to know anything?
I will be presenting you. I think I have what I need. Is there anything in particular that I may have missed?
No. You know me for long, right, Sean? No mysteries.
I double checked with your Wikipedia page.
I found out I had a Wikipedia page.
Wow.
I didn't know. I didn't do it. I don't know who did it. I was very surprised when I have seen that. So maybe
it's pretty detailed. I learned that you had a French language school, that you owned the school and taught.
Oh.
I didn't know.
You did this, you didn't know. Yeah.
No.
Yeah, it was my side job when being a master student. The fellowship was paid once every 3 months. I needed to eat every day. So
Where was this?
I had during my master, I was 23.
But, no. Where was it? In
Brazil. In Brazil.
Oh, in Brazil. Okay.
Yeah. Because actually I did my master at the same time as I did a degree in French literature during the master in physics. And then since I had this degree, I could teach. I was teaching at Telebras, the Brazilian telecommunications company, in the evenings. And that was very good because I had a very safe salary. And then at a certain point, they didn't want anymore to make a contract with a private person. They wanted a school. I said, okay, then I make a school. So that's how, how it came.
Nice.
Long ago.
Did you sell the school or did you just close the school?
No, I had to sell when I got the job because I got a permanent position in Bauru at UNESCO. And then I had to move and then I sold my part. I had 2 partners and then I sold to one of them. But the guy was not a very good manager. He was very good in French, but not a good manager. And then they had bankrupt a year after I left.
Oh, no.
It was a pity because we started so strong and so well.
Well, at least you should feel good that you sold well before it got belly up. So.
That's right. But I had to sell. I would have liked to continue that.
Yeah.
And how are things going there? You were going to the university or not at all? How is it?
No. Oh no, the Southern California now is a complete shit show. Oh, excuse my. I think that is a technical term that describes the what's going on here, but it's basically the epicenter of COVID in the US right now.
I see. Let me ask you a question. Sorry to change subject. How long should I talk? Give me a minimum and a maximum to make sure I don't get out.
I mean, the colloquia are usually scheduled for, around an hour. So, anywhere like 40 minutes to an hour range is probably
Okay.
it's perfect. Yeah.
Okay, but so if I talk like for 55 minutes, it's bad or it's
That's
okay?
no, that's pretty much ideal actually.
This is ideal.
Yeah, like 50 to 55 minutes, I'd say is ideal, and then yeah.
Okay, very good. I try my best because
I mean, sorry, I answered instead of John. John probably has a different opinion, but
No, I think that's fine. That's perfect.
yeah, okay, very good. Because in the Netherlands, it finishes at 5 o'clock and everybody has to pick up the kids at the kindergarten precisely at 5. So if it gets already from questions 2 minutes beyond 5, they are all very nervous.
okay.
That's why I'm asking, depending on the place. In Germany, it was very relaxed, but since they had to pick up
Now
kids,
they're all at home, so.
they are all home.
If like, don't you think if that were an issue, you should just start your talks half an hour earlier, or maybe an hour earlier, or is that too radical a thought?
I don't know. They have the times, and you can't start 1 hour earlier because the rooms are distributed according to certain. It would have to be 2 hours. Oh,
Sorry,
it's not mine, right?
my phone. And John, afterwards, do you want to take the questions or should I do it? Doesn't matter.
I mean, that's up to you, certainly. I mean, I think I guess people will just ask the questions, right? And then Cristiane can answer.
Okay. So how is the public? What kind are there students? How?
Yes, there are students.
There are students.
There are graduate students. So.
Okay, good. I will be pedagogical then. And you have restarted this week?
That's
after
right.
Christmas
Yes.
break?
Yeah.
Yeah, we just got started again this week.
And when do you finish? You have terms, right? It's not semester. How is it?
Yeah,
Right,
we have quarters, which is the
Quarter.
same as terms, I guess.
Yeah.
And so there are 3 of them, and this is the second one that just started. It typically ends at some point mid-March, and then the last one goes from like roughly from the 1st of April to early June.
Okay.
Did her undergraduate studies in Brazil, in the University of Campinas. And then she did the so-called sandwich PhD, where the different layers of the sandwich were University of Campinas and ETH Zurich in Switzerland. She was a postdoc at the University of Hamburg. She became a professor at the University of Freiburg. After that, after winning a very prestigious professorship from the Swiss National Science Foundation, that comes with not only prestige, it's given to only 2 or 3 people every year, but with a substantial financial award, 1 million Swiss francs. What else? And now Professor Morais-Smith is a professor at the University of Utrecht in the Netherlands. Her awards and honors include receiving a Dresselhaus Prize from Germany, and also the Emmy Noether Prize from the European Physical Society for her various contributions in condensed matter physics and atomic molecular optical physics. Finally, I want to also mention that the COVID-19 pandemic has affected all of us in different ways. And knowing a little bit how much it has affected you, Cristiane, and your family, I just want to say how deeply thankful I am for you taking time out of your out of this difficult time to give us this talk. Okay, let's welcome Professor Morais-Smith.
Thank you. Thank you very much, Shanwen, for this very kind introduction. It's a great pleasure to be with all of you today. And I will try to tell you a bit about the things we have been doing during the last years. So when we think about Feynman's legacy, it has been enormous. And besides the very known ones in QED, path integrals, or Feynman diagrams, there is one that took a while to be recognized and how important it was. And this is the contribution on what is called quantum simulators. Nearly 60 years ago, Richard Feynman gave this talk in which he pronounced this very provocative sentence telling us that there is plenty of room at the bottom. And he was inviting us to do not only understand matter as it is there, but to create, to engineer matter in a way that it might be interesting to us. And to also, when we look at reality, we write models that we have to solve these models and we don't even know whether they are really adequate to describe a certain experiment or a certain physical reality. So he was proposing, let us create experiments and matter in a way to quantum simulate models that are interesting. So it took a while until people realized the importance of these ideas. And nearly 40 years later, like 20 years ago, the field took off with cold atoms in optical lattices with the simulation of the Bose-Hubbard model. And a few years later, with photonic systems that are now quite nice to engineer several kinds of models. But the question is that in these fields, you have atoms or photons, no electrons. And in a world where most of the technology is based on electronics, you wonder, shouldn't we try to build quantum simulators with electrons? So that's what I am going to tell you today. The key ingredients for our quantum simulators are going to be three things. The first thing, we are going to use surface states, Shockley states of metals, like for instance, copper. The copper 111 surface on which you have a 2D electron gas on top of it at the surface. Then we are going to use a scanning tunneling microscope for three different functions, as I will tell you in the next slide. And the next thing that we are going to use are hundreds, many hundreds, 400s of carbon monoxide adsorbates on top of the metallic surface. And with this, we are going to build lots of stuff. So let me just tell you a little bit about the scanning tunneling microscope. This consists of a very sharp tip that finishes with a single atom. And you are going to scan it over a sample to which you connect via a voltage. And you will measure the current that's going through from the tip to the sample or vice versa. If you do this, when you scan this tip on top of your sample, if you try to keep this current constant, and suddenly you have something on top of your sample, you will have to lift your tip to be able to keep the current constant. So in this mode, you will be able to see the topography. You take topographic images of your sample. You can also do something else. You can also measure how the current changes as a function of the voltage as you tune the voltage. When you measure the GIGV, the variation of the current as a function of voltage, you will be able to probe the density of states. So you will get, when you are probing occupied states, you will have electrons tunneling from the sample to the tip. And otherwise, if you are probing empty states, electrons tunnel from the tip to the sample. And you can get a view of the local density of states. Locally, you can see which are the available states. And we'll use it also with a third function, which will be we will put adsorbates here on top of the system, and we will use this tip to move them. That is the third and last common function for the STM that we are going to use. You can see here that for the copper surface beyond minus 400 millielectron volts, there is the onset of the surface state, and that's in the regime that we'll be operating. So the field I'm going to tell you about started in 1993 in California, actually, at Alma Dane, with this very beautiful experiment done in the group of Don Eigler. So Don Eigler has been patterning this surface of copper with iron. You see, each of these yellow-red spikes is one iron atom that is patterned on top of this 2D electron liquid, is the blue region, forming a coral, a circle. And now what you are seeing here inside is the quasi-particle interference with the waves that are being formed like you would see in the sea, with the difference is that these are electronic waves. So this is a quantum coral. And as part of the publicity for their work, they have been writing IBM with the xenon atoms, 35 xenon atoms. And they made this beautiful movie, which is the smallest video ever made. You can see it in YouTube, a boy and his atom. So each pixel here, each of these white pixels is one atom that is being put on top of this 2DEG, and you then do the entire animations. The separation between these two white pixels is 1 nanometer. So it is fascinating. That's why it's the smallest video ever. So this marks the opening of this field of confinement of electrons and looking at this quasi-particle interference. And if you try to understand that, you can do it on very simple terms. If you look at a particle in a box and you solve it as you do in the first year of quantum mechanics, you will see that you can have, depending on the number of nodes, all these solutions. And now, if you look at the experimental measurements of the local density of state maps that you would have with your corals, and you compare with this exact solution of a particle in a circular box, you will see that you can already get a very nice agreement. So it's very simple physics with these very nice experiments that can be used to probe what we are getting there. So now, how to go from the coral to a lattice? So the first thing that you should realize, I am patterning here in orange the copper atoms, okay? And in black, these are the COs that I can pattern on top of the copper. And here you can see the scale for the nanometer. So what happens is that if I make this coral of a certain size, I get my energy level. If I make it slightly larger, this energy level goes down. So I can manipulate the places where the energy levels are positioned depending on the size of my structure. And of course, when I get these energy levels, I get the lowest one, but at higher energies, I get also P-orbitals, P, S, P, G, F, I can get all of them. So now you go from a single coral and you try to put two of them together. Yes?
What?
Yes, is there a question? Sorry, I think there was something there, but it's not a question. So let's go on. So if I now build two of these corals together and I allow for hopping between these two artificial atomic sites, I know that my energy level will split depending on the tunneling, right? I move the energy by E plus T or E minus T. And now I also have the freedom to confine this structure more or less. So depending on how I position this last CO here, I will make my barrier stronger or weaker, and I will shift these energy levels that are shifted by the hopping further or less. So I am getting a tool that I can control pretty much what I will construct. And it was based on this realization that the group of Hari Manoharan did then this extremely beautiful experiment. Let me get rid of my laser. And so they did this extremely beautiful experiment in 2012, in which you see in yellow the copper surface, in brown you see the carbon monoxide. And what he did, he used the tip of the STM to pull all this carbon monoxide into a triangular lattice. And these are like little barriers, like little mountains And then the electrons have to go around this triangular barrier. These barriers arrange in a triangular lattice, and they form artificial graphene. And it is extremely nice because if you look at here at this density of states, you would have precisely the same picture with graphene, with the difference is that this bar here is 2 nanometers, so it's 10 times larger than graphene. It's extremely perfect. If there is any mistake, you can see it, you can correct for it. So it is a very nice tool. And here, the experiment of HOTIS together with the experiment of Don Eigler have been these 2 milestones in the field that have brought us where we are. And if he looks now at the GIGV as a function of voltage, you see here this V shape around zero energy, which is simply probing the Dirac cone, the upper part of the Dirac cone. And when we got there, it was at this point, there were 2 things that were interesting in this experiment. One is that you can only position the COs on top of copper, and the underlying lattice has triangular symmetry. So he was patterning a triangular lattice on top of a triangular substrate, what you can do. But the question we had was, can we use this technique to pattern other kinds of lattices? Because if we can only do triangular or honeycomb lattices, we don't go very far. So that was then our aim, to go beyond the graphene. And we have been doing a lot of things. This is then the outline of my talk. The first work that I am going to tell you, we did it in 2017 when we built a Lieb lattice, so which has a square geometry. After that, we went on to control the orbital degrees of freedom, and I will tell you how we do this in space and in energy. After that, recently we found out how to generate flat p-bands by controlled engineer. And then we went on into controlling topology, how to control the edge states in a Kekule lattice, and we have been generating the first dipolar higher order topological insulator in a Kagome lattice in 2019. And finally, we went on to control the dimension, and we have built the first quantum fractal. It's a very ambitious proposal. Let me try to at least give you a taste of the things we have been doing. Okay, the first one, controlling the geometry. So what we do, I have a theoretical group. We do the concept, what should we detect? Then we do the entire calculation. We pass the design to the experimentalists, and then they build. They are built in the group of Daniel van Mackelberg and Ingmar Zwart. Ingmar is the specialist in STL. Many works have been done by Marluis Lotte's first author. She's now in the US. She was a PhD student at the time. So the first thing that when they came to me and they asked, what could we now measure? I said, okay, Lieb lattice. What is the Lieb lattice? This is a depleted square lattice. You see, it's a square, but there is a blue one missing here in the center. I love this lattice for many, many reasons. The first one is because it's the true lattice of high TC cuprates. In the copper oxygen plane, although people describe it as a square lattice, actually you have copper sitting in the blue sites and the oxygen in the red sites. So the perovskites, they have this structure. It is a lattice that has 3 sites per unit cell. So it goes beyond the paradigm of graphene with 2 sites per unit cell, which is described by a pseudo-spin 1/2. This one is a pseudo-spin 1. It has the 3 bands, so it forms a Dirac cone, and it has a flat band in the middle. So that's quite interesting. And the other thing that I find it so interesting, it's because the sites have different connectivities. If you look at the blue sites have 4 neighbors, but the red sites, they have only 2 neighbors. So it's a very particular lattice. The corner and the edges are inequivalent, okay? It's quite nice that we have this E versus K structure, because if you try to probe with an STM, the flat band would give you a very high signal. It would have a very large density of states. And the Dirac cone, as we have already seen, it should give us a V shape. So it should be easy to probe with the STM. So that is then what we went on to build. You see, what do? You take a box. These are the COs that we are putting around to confine the structure. It's a finite size structure. And then we have to try to build a Lieb lattice. How should we do that? So we tried to put 5 COs here, because then the remaining holes between the COs, it's the anti-lattice where the electrons are going to sit down. It's going to be the red and the blue sites here in between. And then what you do is that you put your STM here, you put your tip on the blue side and you start measuring the GIGV as a function of the voltage that you have to renormalize by the GIGV without any CO. And if you are on the blue spot, you take many blue spots and you take the average, you would see this kind of V-shaped structure. And if you sit on the red spot, you would see this peak, which is the signature of the flat band. And then, so we are going to do 2 types of calculations for that. But what we want is that this finite size structure would be reproducing an infinite lattice with periodic boundary conditions described by some tight binding model. And when we do this kind of calculations, we get this figure here underneath. So we can capture the main features which are being observed experimentally. There is no point to try to reproduce details because they are not even reproducible in experiments. Okay, so the kind of, yes?
I think Kirill has a question.
Yes, please.
Yes, thanks. I was actually even typing my question in the chat as we spoke. But anyway, my question is there a simple way to understand the origin of the flat band? Just normally, I know that flat bands that appear in, let's say, a Kagome lattice or something like this are results of, well, so they always tell you that the electron wave functions are localized because the Fourier transform of something local is flat. And that normally results from some destructive interference, so the electrons cannot get out of a site. But here I don't see any reason for that. So, is there a simple way of?
Yeah, so most of the time, flat bands appear on lattices which have sites with different connectivity, except for one example. So there is, I will also show you a completely different, that was what I knew when we did this work, that sites, lattices with sites with a different connectivity usually have flat bands. One thing I have to add, the band is only flat if your T prime is 0. T prime is the hopping here between red and red. Our band is not flat because we have a sizable next neighbor hopping, okay? So it's not perfectly flat, but...
Well, sorry to interrupt, but when it's flat, when you kill the red to red hopping, do you know where the electrons are stuck? Are they stuck on the blue sides or the red sides?
So here what you can see is that who is generating the flat band is the red side. The blue side has no contribution for the flat band. They are generated specifically by these red sites, which are the sites with only 2, which are depleted in terms of connectivity because they have only 2 neighbors. Okay, that you can see out of the experiment. And the Dirac cone is generated by both the red and the blue. That is something you can detect out of here. But I will show you in a minute also how to generate flat bands in very different manner. Okay, you're welcome. Okay, so the kind of calculations that we are doing are the following. The first calculation that we are doing is what is called a muffin tin description. You see here there is a tin and there is an inverted muffin tin. And here in between you will have your liquid, your electron liquid moving. And each CO is going to be this little mountain. So this would be forming a square lattice, okay? And you know the effective electron mass, you know the diameter of these barriers, 0.6 nanometer, you know the height, it's 0.9 electron volts, and you can simply solve Schrödinger equation for this specific geometry, for in our case is the Lieb lattice, and then you will find the energy levels. But then the question is this finite size structure reproducing a true periodic or infinite model that you would describe with a tight binding description. So then what you do is you calculate the bands in a tight binding and you try to merge them with the energy levels that you are getting out of these finite size calculations. And out of that, you will extract the T and T prime values, such that you can try to attempt to describe your measurements with a tight binding, as I did in the previous slide. Okay, so that's the first surprise we had. Our finite size samples are nevertheless capturing the features of infinite lattices. Okay, so after we have built that Lieb lattice, we thought, okay, what else can we do nice with this Lieb lattice? And the answer that we found that would be very easy with the kind of setup that we have, it was to try to control internal degrees of freedom, like the orbital degrees of freedom. And this work is a shared first authorship by Marlou, who did the experiments, and Sandra Kempkes, who was a PhD student in my group, who did the calculations. So what you realize is that to detect things at a certain voltage is very easy with an SGM. You just tune a button and you detect the features, the local density of states at a higher voltage. And you will see that if you are at low voltages where you have these white spots, which means a very high density of states, because you had S-like states here, when you move to higher voltages, you will start having nodes. You see, we have a red square for you to see, for instance, here that you have a very white spot. Now you have a black, which means you are going into P bands. And indeed, if you calculate the energy as a function of the high symmetry points in our Brillouin zone, I hope you can see my cursor. Let me go back to my laser pointer. If you look at the energy as a function of the high symmetry points in our Brillouin zone, you will see you have 3 bands here, which are S-like, and then you have 6 bands, which are P-like bands. And if you come to 500 MeV, you are probing the P bands. So here on top, you can see now I zoom in one of these unit cells of the experiment on the left and the muffin tin calculations on the right. And indeed, where these green spots are, when I was at -50 MeV, I had a very white, sharp peak there. And now I have these dark nodes because it's the nodes of the PX, PY orbitals. So I can access very easily the p orbitals, but I have px and py in all the 3 sites. The question we had is, can I control, can I decide which orbital goes to which site? I can, but for that, I have to change the design. And the way how we have changed the designs is that instead of having the 5 COs here in the center of my plaquette, as I had before, now we have 12, 4, 4, and 4. And you only realize afterwards, but if you should repeat this experiment, we should have added 1 more here and 1 more there, because these 2 yellows are spurious, you don't want them. We should have put 14, actually. And it's quite nice, because now I can see that the corner side has px, py, but these side sites here, they have only py and only px, because there is no space for having a py here anymore. So this is what you detect experimentally at 70 MeV, and this is what you calculate out of the muffin tin calculations. So it's quite nice. We can decide which orbital goes to which site. But in terms of energy, our energy is still degenerate. The px, py, they still have the same energy. And now we would like to lift this degeneracy. So how to do that? Well, the way to do that, it's actually quite simple. We build a different lattice where we now break the C4V symmetry of the lattice. It's no longer a square, because of course we are patterning things on top of a triangular substrate. Our square is never perfect, but it's almost perfect. But now we voluntarily build a rectangle. You see that the pink is much larger than the blue. And when you do that, you break the symmetry. And now you will see that at plus 50 MeV, you are going to detect only px orbitals. These are experiments, and on the right, you see the theory. And when you come to minus 50 MeV, you have only the py. So this is in a way equivalent to the Zeeman experiment. So Zeeman realized that the spin up and the spin down had degenerate energies. And if you would apply a magnetic field, he could lift this degeneracy by the Zeeman gap. We are lifting the degeneracy of the orbital px and py, not with a magnetic field, but by breaking the lattice C4V symmetry. Okay, so we can control orbital degrees of freedom quite nicely. Okay, after that, we went on to try to understand how to manipulate P bands. And since there is this high excitation in the community about the flat bands that you can generate on twisted bilayer graphene, we were wondering, can we generate flat P bands? And the theory was done by Jette van den Broek, who is a PhD student in my group, and the experiments were driven by Thomas, who is a PhD in the group of Daniel. So what Jette realized is the following. This first design here is the configuration used by Hari Manoharan. So each of these black spots is one CO, and you are forming an artificial lattice where the electrons are sitting on these gray sites, which are here. And if you look at the energy, you see here, this is the Dirac cone at the K point. However, if instead of putting one single CO to do the confinement in your triangular lattice, you put now a rosette of COs with 6 COs, you change completely the structure. And look at your band structure now. You will get the Dirac cone at the K point, but you start to see these p orbitals, they get shifted down, and you start getting a flattish p band here, and a p-type Dirac cone also here in yellow. And then she realized if instead of making one row of rosettes, you make a double layer of rosettes, so lots of COs, look at what happens. You can split the P band, you can separate them in energy from the S bands. So you can access purely P bands without being contaminated by the underlying S bands. So she even calculated it for 3 rosettes, which was fascinating. This gap increases even further, your flat band gets completely flat, but it was too difficult to build experimentally, so we decided to go for that one. And these are the theoretical predictions, what you would measure in the local density of states. For your flat P band, you would see this huge peak here, and you would see this V shape for the S-type Dirac cone and the P-type Dirac cone. So we did that. And here on top, you can see the experiments. You indeed see the S Dirac cone, this very flat P band in violet, and the S and the P Dirac cone down here. And this agrees quite well with the theoretical predictions. So now it comes the next step, which would be to gate, to be able to induce interactions into this type of structure, to study what kind of physics would emerge in P bands with electrons that would be interacting. Everything I tell you here is no interacting, okay? Okay, so after controlling the geometry and the orbitals generating flat P bands, you would wonder, what else could we do that could be cool to try to realize? And the answer would be topology. So the first thing we tried to build, and this was in 2019, it was a dipolar version of a higher order topological insulator. So the main players here were Sander Kempkes, my PhD student, and Jette van den Broek, both doing the theory, and Marlou doing the experiments. So what did we do? First, before I tell you precisely what we did, let me just explain for the ones who don't know what a HOTIS is. So a HOTIS is the following. You probably heard about topological insulators. So these are materials that are simultaneously insulating in the bulk and metallic at the edges. And if you look at the gap, at the bulk gap, you would see states crossing there, and these states are the ones localized at the edge, which are metallic. And usually, if my bulk is d-dimensional, the edge modes have one dimension less. These are unusual topological insulators. But what is called a higher order topological insulator has been proposed, on which your edge modes are at least dimensionality 2 lower than the bulk. So if your bulk is 2D, your edge modes would be 0 dimensional, corner modes. If you would be in 3D, you could have corner modes or hinge, one-dimensional hinge states. Okay, in this case, if I have my corner modes, they will be localized 0 energy modes in the middle of my spectrum. Okay, so the proposal for HOTIS, they were proposed for quadrupolar structures, and I am using the word HOTI here just in the sense that I am generating an edge mode which has dimensionality d-2. And this might happen also for structures which are dipolar-like. Okay, so if you try to think what kind of lattice could be interesting to build, there were these predictions by Ezawa. If you would take a Kagome lattice and you would build a breathing Kagome lattice, which is like an SSH model, which has dimerized hoppings, and if now your corner mode, your corner site is isolated because TA, which is the one here, connecting these 3 last sites is 0, you should have a 0 mode. If you have a trimer being formed, you would be in a trivial state. But when TA is non-zero, but is smaller than TB, you should still observe this topological 0 mode. And that is then what we went on to build. So this is our Kagome lattice. It is a lattice consisting of triangles which are looking down and triangles which are looking up, separated by these hexagons. The corner sides I am painting in blue, the bulk in green, and the edges in yellow. And we are going to build 2 types of lattices. And if you take a careful look here, you will see that, for instance, here inside this red triangle, there is only 1 CO. And here I have 4 COs. This is what is modifying the barrier for the last hopping here at the corner. You see here, this hopping is weak because I have lots of COs here. Whereas here, this hopping is strong. I have only 1 CO, okay? And now I am going to sit at the blue, the green, and the yellow sites, and we are going to take the GIGV maps. And on top here, you see the experimental, and down you see the theory. So if you're in the trivial lattice, no matter where you sit, you always detect the same thing, the same with the theory. But if you are in the non-trivial lattice, when this last triangle is weak, you will see that the green has 1 peak here, another peak here. There is some overlap. This is the minimum. And then right at this minimum, the blue has this peak here, maximum, okay? So that is then the theory. And now you are going to sit precisely where this maximum is and try to understand how is when you scan the entire sample to look at the local density of states. So look first on the right-hand side where you look at the experiment in the trivial phase. Bulk and edges and corner, they are all the same always. But on the left column, if you look at -110 MeV, you see red here in the bulk. It's when you have the strong weight, it means high density of states. At 5 MeV, you see that this now has moved to the edge. And you can see the comparison with the theory here in the middle. And now at 50 MeV, the weight has moved to the corner. So you have the corner states, okay, inside the gap. They are not at 0 energy because we have an on-site energy, which is precisely 50 MeV. It's the renormalized zero of the zero mode for us. So now we start voluntarily creating defects in our structure. And when you create a defect here, what you will see is that your corner modes resist at the other corners, although I have killed that one. Now, if you add a protrusion with 120 degrees defect, it doesn't affect my corner modes, they remain there. But if I add a protrusion which has a 60 degrees defect, I add 1 zero mode. So it is very nice because we can manipulate the zero modes at will by design. Okay, so after playing with the HOTIS, we thought what kind of topological state we would like to probe further. And we decided to go for something that's quite different and that was challenging our understanding of topological states as we knew them from the quantum Hall and the quantum spin Hall states. And I will tell you in a minute what this is. It's the a dependence on the boundary, on the type of the boundary to decide the topology. The main players in this work were again Iete, who is my student doing the theory, and Sarsha doing the experiments. So what is this? We are going to build a Kekule lattice. What is a Kekule lattice? It's a graphene lattice in which I have now dimerized the hopping. The hexagons will have a hopping T0, and the bonds connecting the hexagons to the next ones have a hopping T1. And these two things are different, okay? So now, depending on the kind of the edge that I have, I will observe different physics in terms of topology. And we are going to look at three types. We have looked at three, but I will tell you about two types of edges. One is the so-called molecular zigzag. The other is the so-called partially bearded and the armchair. Why do we choose these odd types of edges? Because I want my edge to terminate with the same number of A and B sublattices. Because if I break sublattice symmetry, as with the usual zigzag, as in graphene and nanoribbons, I immediately get a localized mode because I'm breaking sublattice symmetry. So this is a kind of a trivial effect. I don't want that. I want a more complex type of edge that preserves the number of A and B sublattices at the edge, but they will still have different effects. Okay, that's the reason for this thing. There were some predictions by the group of WHO, which were quite interesting. They say, take a certain lattice that has the hexagon, the hopping inside the hexagon is smaller than the outside one, and terminate by, let's say, this kind of edge. In this case, this lattice is topological, and the other one, if I invert, T1 is smaller than T0, this one is trivial. But now, if I change my edge, the lattice that was topological became trivial, and the one that was trivial became topological. And you would say, what the hell? For quantum Hall samples and for the quantum spin Hall, I know that I can have whatever termination. My topology should be robust to that. It does not matter my termination, right? But here we have topological crystalline insulators. And for those, it matters because the termination determines the unit cell, and they will be topological or not, depending on that. So we went on to check that. And we have been building 4 lattices with more than 400 COs. It's the absolute record of COs. As you can see here, we have to also very carefully screen to prevent these particles to go out of the sample. So we have to add additional confinement here without adding additional on-site potential. So it is already lots of calculations to find out the right way to confine the lattice. And you will control if T0 is large by putting 1 CO here or by putting 6. You will make T0 weak because now you put 4 COs pointing to this region here. And here you point outside. So you can control T0 and T1 in this way. And now we build the 4 types of lattices. Here you see 2 of them. This one has a very strong hexagon with weak bonds in between. And here you see that if I now have the molecular zigzag edge and I sit at the boundaries or at the bulk in black and or in yellow, all the curves are the same. It is trivial. But here, if I sit at the black, that is the bulk, I see the minimum, I see the gap. But if I sit at the red or the violet, I see the peak, right? So I have a topological state. And indeed, when I look at the local density of states, I will see my topological state here and not here. On top, you see the experiment, underneath you see the theory. And now I invert. Instead of having these very thick hexagons, I now get thin hexagons with these very thick bonds in between. And now you see the picture change. Now this one is trivial, and now this one became topological. You see here for the yellow and the blue. And indeed, when I now look, I see here my edge mode. I can visualize the beautiful topological edge mode here and here in the theory. And here there is nothing. It became trivial. So message, topological crystalline insulators will be topological or not, depending on determination, not only on the structure of the lattice. Okay, so now I go into my last topic. I hope I still have a few minutes to tell you how do electrons behave in fractional dimensions. So since we can manipulate the system so well, we thought, let's try to control the dimensionality in the systems that we build. And again, Sander Kempkes was the main player together with Marlou Slot, who did the calculation. Sander did the calculations, Marlou did the experiments. Okay, so the concept of fractals, what are that? I want to go into fractal dimension. This is no integer dimension. So fractals are these beautiful structures that most of the time have the property of self-similarity. As I keep zooming in on the structure, I keep seeing the same thing. One beautiful example is the Sierpinski carpet. So it is a square. I divide it into 9 smaller squares and I cut the central one. I take each of them, divide again into 9 smaller squares and I cut the central one, and so on. And as I zoom in, I keep seeing the same structure. So they have what is called a fractal dimension, a non-integer dimension. How does this come about? Suppose this Hausdorff, it's called Hausdorff dimension. The Hausdorff dimension is given by the log of the number divided by the log of the scaling. Let me explain to you how this comes. It's quite simple. Suppose I have a red line. Now I use a scaling, I make it twice as large. This is my scaling, that is these 2 over here. Now I ask myself, how many of the original ones I can fit inside here? 1, 2, that's the number 2 that is here, because I am in 1 dimension. Look now at this red square. Let us scale it by 2 in the Y and in the X direction. Now you ask yourself, that's the 2 which is here. How many red squares I can fit inside the big blue square? 1, 2, 3, 4, because I am in 2 dimensions. Paint this triangle now completely red. Now scale it by 2. You scale by 2 here, you scale by 2 here, okay? Paint this triangle completely blue. Now you ask yourself, how many of the completely red triangles I can fit inside the completely blue one? 1 here, 2 here, 3 here, and 1 inverted here in the center. I would have 4. I would be in 2 dimensions. But this turns out to be what is called a Sierpinski fractal. And a Sierpinski fractal is a structure in which I take my triangle and I cut an inverted triangle in the center. And I remain with these 3 triangles in which I cut an inverted triangle at the center. So if I have this, and I keep cutting ad infinitum, so if I have this structure, when I do this scaling, I have a missing one in the center, so I don't get 4 of the original one, but just 3. And this is how the 158 dimension emerges. Log 3 over log 2 gives me this fractal dimension of the Sierpinski gasket, it's called. Okay, so fractals are fascinating structures that are closely related to nature and humankind. They appear in the Romanesco broccoli, in the structure of roots, in the structure of branches, leaves, in our lungs, in our neuronal system, even in our heart beating. This is a type of dynamical fractal. And if it's not, if the heart beating is not fractal, we are ill. If it becomes chaotic or periodic, it means illness. They are also very important in science. For instance, if you build here, sorry, how am I doing with time? I have short.
You're doing fine. I think you have
right. Okay,
like
very
10
good.
minutes to do it. Yeah.
Yes. So they are very important. Here you can see this very old type of telephone, which is being built with a fractal antenna. They are quite nice for antennas because since they have small and large structures inside, you can send and receive simultaneously small and large frequencies. They are also very important to build solar cells because these blue regions, these blue plots here are simply fractals in which you are increasing the complexity. If you increase the complexity with which you are covering your two-dimensional structure, you increase the possibility to store energy. They are also very popular in arts. This is the beautiful picture you know from Escher, right? In any ADS CFT talk, you will see it. And they were used in arts since the 11th century after Christ, although only recently people, mathematicians, only in the last century, Mandelbrot has shown how to characterize them. And this is a beautiful Pollock painting, which also has a fractal structure underneath. So we decided then to build 3 generations of a Sierpinski gasket. And that's the way how we did, by using this type of confinement for the first, the second, and the third generation. And we were wondering, do the electrons sitting inside this finite generation fractal knows that it is in a fractal? Can the electron perceive this fractional dimension? That was the question we wanted to solve. So we have been doing again muffin tin and tight binding descriptions. You will ask, how can you do a tight binding description, a fractal now? This structure is not periodic. So there is a method developed by Kadanoff. This would be the site is inside our fractal. It's very beautiful. He builds another mirror image of that, and then he applies periodic boundary conditions between those, and you can then generate some kind of periodic structure out of your fractal. This is what we built. Then we sit at the red, the blue, and the green sites, which have different colors because they have different connectivities. And we take the spectrum, the GIDV in each of them. And now out of that, you identify some interesting regimes. For instance, here at minus 300 MeV, red, blue, and green are all equal. Here at minus 100 MeV, red is low, green and blue are large. And here, sorry, that's minus, yes, minus 100. And here the blue is low and the green and the red are high. So now we are going to fix ourselves at these 3 different values of energy and scan the entire sample. And that you see on top the experiments, and at the bottom you see the theory. This is a kind of a bonding configuration. White means very high density of states, dark means low density of states. At minus 300 MeV, we really have a very clear Sierpinski gasket. Here you see that the structure starts to get partitioned. And here you see this anti-bonding configuration doesn't look much like a Sierpinski. And this would be an insulating structure if you would be able to attach leads to this structure, whereas the first one is metallic. It's because of that depletion in one of the sites that it starts to become insulating. Here you can see the three-dimensional plots. On top you see the theory. At the bottom you see the experiments between the bonding and the anti-bonding. But now the important question is, we are probing with this local density of states the wave function of the electron, modulus psi square. Does it know about the fractal dimension? And to do that, you can use a method which is called Minkowski-Bulligand, or the box counting method. So we take the third generation for any specific value of energy, let's say minus 300 MeV. And now you color your density of states in white and black. You have to decide what is white and what is black, because you have lots of grays in between, and that's going to be some error bars. I tell you in the next slide. But the method tells you, choose a circle or a box of a reasonable size compared to what you want to map, the figure that you want to cover. Here, for instance, this pink one seems reasonable because I can cover the white spots quite well with this pink circle. And now you cover everything and you count how many of these pink circles you needed. And in a log of the number versus a log of the inverse radius of your circles, you will find a point. Now you change the size of your circle, you make it slightly smaller, you cover everything again, you count again how many you need, and you will get another point. And you keep doing it, smaller, 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 larger, larger, larger. And you will find out that all these points are sitting on a straight line. And the slope of this straight line tells you the dimensionality of the object that you are trying to cover. And here you find 159. So the perfect Sierpinski triangle in the infinite limit would have 158. So it sounds pretty good, right? So we did this not only for one energy, but for many energies, okay? And you will see that they are always here around 1.6. If you would do the same for the graphene lattice of Manhattan, it would be around 2. And now you see here these error bars. What do they mean? As I said, I have to cover the white part with the circles, but there are regions which are gray. Is this white or black? So we having to do in some ad hoc manner to decide what we call white. So what we did is we say, okay, let's say a certain percentage of the highest peak you call white, 75%. Every peak which is up to 75% of the highest peak, more than 75%, you call white. The rest you call black. But I could have used 60% or 55%. So the error bars give us a margin around that. But that is to show that you remain around here, even though you have some ad hoc decision on what is black and what is white. And if you apply the same argument to the other lattices, you would get around 2. So the electrons know that they are living in a fractal dimension. This holds even for first and second generations of the triangle. Okay, I will just flash this very last experiment because now this is something else that we did just recently. The paper is still under peer review. It's no longer done with the same type of techniques that we have been using until now, because until now we could only probe the statical behavior of these electrons. Now we were interested in fractals and we would like to probe the quantum dynamics. And this we can't do with the STM. So I got together with a group of Professor Shanming Jin in Shanghai, and Xiaoyun Shu was the main student behind the experiments. And now this is the first realization of a quantum walk in a fractal. So in analogy with this ant in the labyrinth problem of the Gene, I wonder if this is a quantum ant in the labyrinth. And this is, I just flash it. It is a photonic lattice with many waveguides, which is going to have, how do you call, when you cut it, it will have the shape of a Sierpinski gasket. And now you will inject light at the corner and you will see how the light is diffusing through your fractal. It's very beautiful because it's a direct imaging method. And you see what happens with the photons when they meet this first hole here. Suddenly they are finding that there is a void in the material. They start moving around. And what is marvelous to observe is that if you measure the variance, the mean square displacement as a function of the propagation length along the third dimension, which if you divide by the speed of light is the time that these photons are hopping here in this transverse direction, you will see that it starts with a ballistic motion, which doesn't have an exponent 2 because of the size of the sample, because of the shape. And immediately when it meets the hole, it starts changing the exponent and it picks up an exponent, which is precisely the fractal dimension of the object. Here, it is this 158. And here you see it in the numerical simulations, precisely the same. So the photon meets a hole, it starts going around. Immediately when it closes around the hole, it already knows it is a Sierpinski gasket. It has dimension 158 because you observe it into the mean square displacement exponent. So it is amazing. I think I am coming to the end of my presentation. I still have a movie. I can refer you to look for that in the YouTube, or I can show you. You should tell me what I should do. Should I skip it or should I show? It's very fun. John?
Sure, I'd say, go ahead. Yeah.
Yeah, may I? Okay, I promise you will like it. Let me get rid of my laser. So I am going to play a game with you now. Einstein has been telling us that God does not play dice with the universe. But nowadays, I started doubting. You see, I have been telling you that nature is very fractal, our body is very fractal. Now, I will show you something which comes under the name of quantum chaos game. It's on YouTube. If you just go to YouTube and you type quantum chaos game, you will get it. So let me tell you what I'm going to do. We are going to build a triangle, a normal triangle, and it has 3 vertices. And we want to play dice. But since our dice usually have 6 numbers, I will call one corner 1, the other corner 2, the other corner 3, and I repeat. The first corner, I call it also 4, 5, and 6. Now we will choose one inner point. It could also be an outside point of the triangle, but start with an inner point in my triangle. And I will play dice, and I get a number. And each number I get, I will connect this point to the corner, to the vertex corresponding to that number, and I will pick up a midpoint. And I will collect the selection of these midpoints, and let's see what will happen. So it will repeat the experiment. It's amazing, isn't it? It's a completely random game. I am picking up the vertices by playing dice. And after thousands of iterations, we have a fractal emerging out of the chaos. So maybe God is playing dice, who knows? So I come to my outlook. Everything I told you that we have been building, it's for no-interacting electrons. You wouldn't imagine that one can play so much with no-interacting electrons, right? For the ones working on strong correlations for so many years. Now, this technique can be just brought into semiconductors. It can be patterned in different structures that we could gate to reach some strongly interacting regime, or using different substrates. So we could use, for instance, surface states of 3 GTIs to get Dirac electrons. We could include substrates which are heavier and have a strong spin-orbit coupling. We could include adsorbates that have a strong spin-orbit coupling, and could maybe transfer this spin-orbit coupling via the scattering. We could try to engineer strongly correlated phases in these flat bands, flat P bands that we found out how to build. And we should now try to get a more deep theoretical understanding of topology in fractal dimensions, because topology is something that comes with integer numbers, and fractals come with fractional numbers. How are these things going to merge? What's going to happen? Very probably, this will help us to get interested into fractional calculus. So it's something I had never heard about, but after being interested in fractals, and I started looking up, and we have been recently doing a work. And if you are interested, we have a full review of the history of fractional calculus. It started long ago with very famous mathematicians a few centuries ago, but we are still just starting on that. There is much more to be uncovered there. And I come then to my conclusions. I have been showing you how to build a Lieb lattice and to control the orbital degrees of freedom in space and in energy. I have been showing you how to generate some flat P bands and P Dirac in some artificial graphene. We have been designing and building an electronic dipolar higher order topological insulator in a Kagome structure. And we have been looking at the importance of the edge in determining the topology in topological crystalline insulators that were exemplified by Kekule lattices. I have finally shown you how to experimentally build a Sierpinski gasket fractal. And I have just glanced at how is the quantum dynamics in fractals by looking at photonic lattices, and how smart the photon is to understand that it's living in a fractional dimension by picking up the right exponent. That is the dimensionality of the fractal immediately after meeting the first void in the material. So with that, I would like to tell you that indeed there is plenty of room at the bottom, but I think even more in a fractal. And I thank you very much for your kind attention.
All right, thanks very much for a really excellent talk. I really enjoyed it. Let's see, does anyone have questions?
I have a question.
Yeah, of course, go ahead.
Okay. So, Cristiane, about the Lieb lattice.
Yes.
Well, we are at UCR, so I have to ask you, since and it's the same lattice as the cuprates, yes. Once it's made experimentally, can the Varma phase be created, the circulating alternating currents?
Yeah, that would be great, because of course I have been studying a lot the Varma phase, especially with quantum simulators with cold atoms. We have several works on that. But here, it's very difficult to tune how you move from one to the other, you see. You would need circulating currents, and I don't know how to build that here. With cold atoms, you could, because what you could do, you could shift the potential, and then the charge would simply flow from one to the other. But here, I would not know how to do. It would be great if we could, definitely.
But the electrons can hop around, right?
The electrons can hop around, but you would need more to be able to generate, because it's like a flux, right? So it spontaneously, this would just not form. We need more to form this flux that would be enclosed into the Lieb lattice. We had an experimental setup in the group of Andreas Hemmerich with bosons, which was not precisely the Lieb lattice, but these were lattices with S and P orbitals, and you would hop in between. And then we have an experimental setup for a Lieb lattice. This is a PRL 2016, to try to engineer the Varma phase. And we even had a very interesting structure that didn't have topological properties in the ground state, but had topological properties in the excited state of this Varma phase. But it has not yet been realized experimentally, but we have a proposal about how to do it. It's difficult, but in principle doable. But here it's more difficult, I think.
Okay, thank you. Can I ask another question?
Sure.
When you were talking about the edges, the two different edges, and tuning T0 and T1,
Yes.
I didn't understand, did they have to build two separate systems, or it was the same system, they just...
No. So we have like this. You see, if you look here at this bulk and this bulk, they are precisely identical. Okay? So this has T0 is smaller than T1. T1 is thick.
Yeah, the question is,
T0
can they...
is small. These are two different lattices. We built two different lattices, but have the same bulk. And then we make them with different terminations. And then what you see is that that one is topological and that one is not. And the previous one, we made two lattices. You see, it's the same bulk. This bulk is precisely the same as this, but they have the different termination. And now it inverts. This is topological and this is not. So it's not just the bulk and not just the type of determination that decides who is topological and who is not. It's both together. Because if T0 is larger than T1, this one is topological, this is not. But now if T0 is smaller than T1, this is not topological and this is.
And how is T0 and T1 determined? Is it just geometric?
So like this, let me show you the design. You see here, T0 is the hopping from this side to this side, okay? So that's the red bond. And this hopping is determined. Here there is only one barrier and these three barriers here are open and the other one is pointing outside. So the hopping here is very strong, you see? Compared to the next one, here I put 6 COs and I put 1 CO pointing towards it. So this hopping here is weak because it's confined by this CO and by this large amount of COs here. So this T0 is weak. And this T0 is very strong because there is only one here and it's an open space here. And now here you see there is one, here this T1, which is the black one, is weak because this is pointing towards it here and here. But as here it is open. So here T1 is large. The distance is always the same. It's the positioning of the COs that makes the barriers such that the hopping will be weak or strong. Is it clear, Shaman?
Yes, I was wondering if you could continue to tune T0 and T1 somehow, but no.
No, you have to build different lattices for each of them.
Cristiane, hi, good evening.
Hey, David, nice to see you.
So the Kekule structure is usually around the hexagon, shorter and longer bonds around the hexagon, not nearest neighbors. Why are you calling it Kekule?
Sorry, can you repeat? I
Well,
didn't.
The Kekule structure, you take a benzene ring
Yes.
and you have short and longer bonds
Yes.
around the benzene ring.
Yes.
They're in resonance.
Yes.
In Kekule.
But the short
So
and the long.
yeah, but typically that, so why are you calling, these are bonds outside the ring you're talking about?
So here is the benzene ring, okay? And
Right.
this is the one connecting the benzene rings, the different benzene rings, if you want.
That would not matter in general in benzene.
Yeah, so, but here it does. So it's Kekule with the, in the way that short and long bonds translate into, short bonds means strong hopping and long
Yes, of
bonds
course.
means
Yeah.
weak hopping. But we generate strong and weak hoppings by manipulating the barriers and not the length, okay? So for us, the lattice has always the same length, but we manipulate the confinement by approaching the COs that are making the barriers, the hopping becomes weak or strong. So the
Right.
analogy is not with the distance, with the separation, but is with the strength of the tight binding model, describing the intensity of the hopping.
But, so in site B, all the bonds are strong?
So here in A, the red bonds, they are all strong, and the black hoppings, so these are all hoppings, okay? The red marks hopping from this side to this, which is strong.
But they're all equal. They're all equal.
And they are all strong. They are equal because you see around them you have the same COs in the center, so they are all equal. But the black one is weak.
Okay.
And here it's vice versa. The black is strong because now you see that this, you open the COs. And now the red is weak because you have 6 COs in between. So this now became weak.
Yeah, no, I understand.
Yeah, it's different than our usual intuition, where being further away means weak hopping and being close together means strong hopping. Here it's all controlled by barriers.
All right. Any other questions? If not, then I guess let's thank Cristiane one more time. And I wish we could do this actually in person. But yeah, thank you again for a wonderful talk. It was great to have you.
Thank you. Thank you very much. Very nice to see all of you. Good night.
Oh.
All right. Yeah. Take care, everyone.
Yeah.
Ciao, Cristiane.
Ciao, ciao. Bye.